do you prove that? Function's continuous, the absolute value. Would it help if we wrote down the definition of continuity at a point? Is that going to be enough, right? Right. These various things. Where all epsilon greater than 0, there exists a delta, which depends on epsilon. Thank you very much. Such that whenever x minus the point at which we're claiming continuity exists, that implies the difference here is less than epsilon, right? So this is supposed to be less than delta of epsilon. Sorry. So whenever I'm real close to x naught, perhaps even x naught, I mean that this condition allows you to be sitting right on top of x naught, right? In which case it would be 0, which is certainly less than any positive delta. Once I get close to 0 here, this gets close to 0. That's the argument, right? So, well, what do you have to show? If f is continuous, then this is true. We want f absolute to be continuous. Then, this would have to be true, right? That would have to be true. Now, who was it? Matt wrote down the triangle inequality difference version, which says what? Is that true? So if the function is continuous, then this thing can be made less than epsilon with a pseudo delta. And this dominates this thing, right? Which makes it less than epsilon. But that's continuity for the absolute value. Correct? By the way, why don't we just stop for a moment and prove the difference version of the triangle inequality. So the triangle inequality says this, right? Given that, why is it true that that's true? That's the fact we're using here. That'd be a good test question. Well, you know, what if you did this? Let y equal z minus x. Then you would have x plus y absolute equals absolute x plus z minus x, which is z, right? But then by the triangle inequality applied to this, I'm going to have to start another conjunction. You could say this. You could say that x plus c plus the absolute value of minus x is greater than or equal to the absolute value of x plus z minus x equals c, right? Certainly say that. This is plus x. So, let's see. Well, all you have to do is turn this around. Why don't we do this? Make this minus c. minus C, absolute value minus C is still plus C. And then take this to the other side. Okay? Now, since this is an absolute value, it's going to be greater than whether this is positive or negative, right? So it can just as well be that, which means we might as well just do that. And that's what we want, right? And then you don't like these algebraic proofs, you can always just do cases. You know, just consider all numerical cases. Okay, so now we have proved what is in 2.2.2 there. We have the criterion for Cauchy integrability of a function, and coincidentally we notice that the function as it's defined there, the absolute value is integrable, but the function is not. So if the function is continuous, the absolute value is continuous, so both will be Cauchy integrable, but not vice versa. Okay? All right. Now, let's see if we can come up with the fundamental theorem of calculus, Cauchy style. What is a fundamental theorem of calculus? It is a statement about two things. The existence of a definite integral. It's one. Two, a method for evaluation. So, we would like to start out, what's theorem 2.3.1. If f is differentiable on AB, and f prime is continuous on AB, i.e., f is C1 on AB, right? Because it has a continuous derivative. By the way, what's it mean to have a derivative but at an endpoint? You're not allowed to go to the left of A or the right of B. Exactly how do you take a two-sided limit and define the derivative? What do they mean? What is implicit in all of this that nobody's saying? It has a lateral limit, right? The limit from the left exists in B, and the limit from the right exists in A. So the continuity, the existence of the derivative, and the continuity of the derivative is governed by that, by the lateral limit. That's usually the understanding. Some books, they say if it's continuous on the closed interval and differentiable on the corresponding open interval. You see a lot of theorems phrased like that. What they really mean here is that you can extend the derivative to that last point just by taking its limit there and the other ones. And you don't really care what happens outside of it. Then you go to hell completely outside, as long as you have this property inside. So if that's true, then what? Then two things happen. First of all, one, f prime is Cauchy integrable. And two, this is the real extra part of this deal, the Cauchy integral from a to x of f prime of x dx. Does he use? No, he uses t. It's always good to use a different variable than the variable up here, the variable root function. Integration should be different than the upper limit. Is equal to f, the primitive of f prime evaluated at the upper limit minus the primitive evaluated at the lower limit for each x in AB. So that's a statement of the fundamental theorem of calculus for Cauchy integration. A lot of this stuff we will just be able to retain lock, stock, and barrel over to the Riemann chapter 3. So what's the difference between a Cauchy integral and a Riemann?
tags?
The tag is allowed to be anywhere instead of at the side. That's all. We will find, as I said, the condition here for Cauchy integrability will just be the condition for ring integrability as well.